Welcome to video lecture B2. This one is on vector subspaces. Here are the outline and objectives. We'll define something called a vector subspace, which, as you might expect, is a vector space that lives inside another vector space. And we'll analyze whether, I say given subspaces or not, but I really mean given subsets are subspaces or not. Sorry. And then we'll demonstrate that the span of any set of vectors in V is a subspace of V. So if I've got a bunch of vectors and I look at their span, the set of all linear combinations of them, then that should be a subspace. So here we go. Here's the definition. A vector subspace, informally you want to think about, you've got some blob of a subspace here. You've got some big vector space here. And a vector subspace is going to be something that just lives inside of it. So W lives inside V. Okay? And here are the three axioms that, or I guess I'm calling this H. So instead of W, let's call this H. Right? So what are the properties that H should satisfy? Well, it should contain 0. So whether I like it or not, I'm going to have a 0 in there. So there's the 0 vector. It also needs to have the property that if I take U and V inside H, that their sum stays inside H. And it should have the property that if U is in H, then when I rescale it by any real number, that I stay inside H. So there's a way in which this blob is not a very realistic picture, because it's clear that just geometrically I could take some vector in here and rescale it and end up outside. So really, a vector subspace might look like a line in R2 or R3, or a plane in R3, something like that. So we'll see some more examples in a minute. But so those are the three things. It has to be closed under addition, closed under scalar multiplication, and it has to be non-empty. And that's what this just checking for 0 is equivalent to checking that it's non-empty. Because if I had anything that was non-zero in it, then I could always multiply by the 0 element, the 0 real number, and get 0 that way, because that's one of my axioms. OK, so what are some examples? Well, if I just take the set 0, if that's my whole set, that'll be a subspace inside my vector space. Because if there's only 0, then I can only add zeros, so I only get 0. And if I rescale 0 by anything, I still get 0, and 0 is in there. OK, so this is sometimes called a trivial subspace. It's there, and it's important for statements of theorems, but it's not the most interesting subspace on the block. So here's another one. I could look at the set of all things. So I'm in a R3, but I only look at vectors that have a 0y component, right? So if you're thinking about, if z is going up and maybe x is coming out at you, and y is going that way, then I'm looking at things that only have components sticking out at you and going up, right? And so that would be a plane in R3. And now P3, I need to tell you what P3 is. So P3, I'm going to define to be just the set of all polynomials of degree less than or equal to 3. So it's the set of all a plus bt plus ct squared plus dt cubed, such that a, b, c, and d can be any real numbers. So that's a subspace of the space of all polynomials of any degree. And why is this a subspace? Well, 0 is in here, right? Because I can just let a, b, c, and d be 0. If I add two polynomials of degree 3 or less, then when I add them, I'll just be adding their coefficients component-wise. I'll still get a polynomial of degree 3 or less. And finally, if I rescale a polynomial degree 3 or less, well, all I'll be doing is multiplying each of these coefficients, a, b, c, and d, by k. And that'll still be of the form something plus something times t plus something times t squared plus something times t cubed, where those values are there. OK, so those things are all three good vector subspaces. And now let's take a look at a bunch of other possible examples and try to make sense of them. So for example 1, I'm asking about the set of all a such that a is a real number. that lives inside R squared. And that one's not so hard to draw, right? So this is example 1. I can draw a copy of R squared pretty well. And now if I look at the set of all AA, then I'm just going to have, oh, this marker isn't working very well either. Kind of striking out these days. Okay, so then this is the set of all points of the form AA, and so that's just a line in R2. Okay, so this would be H living inside R2, and so that definitely is a subspace. It has 0. If I add two things along this line, if I add AA to BB, right, AA plus BB equals A plus B, A plus B. So that's also of that form. If I multiply something like this, I'll get CA over CA. So that's also of that form. So you can see it both algebraically and geometrically. OK. Suppose I think about the set of all F from R to R such that F is differentiable. Where would that be living? Well, it's going to live inside the vector space of all functions from R to R, which we saw earlier. And saying it's differentiable is just a property, right? So how does that property behave with respect to the subspace axioms? Is 0 a differentiable function? Sure, the derivative of any constant is 0, including the 0 function. If I add two differentiable functions, is there some differentiable? Right? So now you need to use something along the lines of, well, we know that the derivative of the sum is the sum of the derivatives, right? So if f and g are differentiable, then f plus g also is. And we also know that, that if I multiply f times a constant and take the derivative of that, the constants pull out. Okay? So that means that if I have any function in here, that the sum of any two functions is in there and any scalar multiple is, so therefore this is a subspace. Okay, so we're doing pretty well here. How about the set of all 2 by 2 matrices where I have that have this form? So I can have anything I want on the diagonal, and the thing up here has to be A plus B. That has to be 0. What happens if I add two matrices that look like that? So this is for 3 now. Well, if I have, I guess I'll call this A1 plus B1, 0, B1, and I add it to A2 plus B2, 0, B2, then do I get something that's of the right form? Well, it looks like I'll get A1 plus A2, and then here I'll get A1 plus A2 plus B1 plus B2. Sorry, I didn't quite have room for that there. Then I have 0, and then I'll have B1 plus B2. Okay? So that's the right form. It's of the form anything, anything, and then that sum up there. So it's closed under addition. And scalar multiplication is even easier, right? If I multiply through everything by C, then I'll have C times A, C times B, C times A plus B, which is CA plus CB. So, okay, so that's another good one. How about the set of all vectors of the form AA squared such that A is a real number? All right, so that would be looking more like, so if it was going to be a subspace of anything, it would be a subspace of R2. But now I'm looking at the set of all things that look like AA squared. So that means going out A, I have height A squared. So that's just this parabola. So is this parabola, well, it does contain 0, right, if A equals 0. So that's the first thing to check. Now, you want to check about scalar multiplication, right? If I multiply by C, then I get CA squared. I get CA, and then C times A squared. But that probably, even just 2, right? If I have 2A here, then what should go here is the square of 2A, which is 4A squared, not 2A squared. So it's pretty clear that this isn't preserved by scalar multiplication, right? So if I have, so for example, 1, 1 is an element of H, but 2, 2 is not an element of H, and so that's bad because I should be able to rescale 1, 1 by 2. So this illustrates something, which is that if you want to show something's not a subspace, you want to give the best way to do it is to give a concrete numerical example where the reader doesn't have to do a lot of work, right? Just 1, 1, definitely in there when a equals 1. 2, 2, no way for that to be in there because if a equals 2, then a squared is 4. But 2, 2 is 2 times 1, 1. Okay? So therefore, it doesn't satisfy the closure under scalar multiplication axiom. All right, example 5. So here are all the polynomials which have the form at squared plus at plus a. So t squared plus t, or 2t squared plus 2t plus 2, 3t squared plus 3t plus 3, all the things where it's all just one coefficient there. What do you think of that one? Well, if we added something like this to something with bt squared plus bt plus b, then we'd get a plus bt squared, a plus bt, and a plus b. So it would still be the same coefficient in front of everything. Okay, so it's closed under addition. Similarly for scalar multiplication. Now how about this one? Example 6, p of t equals t squared plus at plus b. Right? What doesn't work here that worked before? Well, in number 6, if I add, say, t squared plus 2t plus 3, and I add it to t squared minus 2t plus 4, what do I get? Well, I get 2t squared plus these cancel plus 7, right? So these things are certainly in this vector space, this potential subspace H, this subset. But this thing is not, because everything in the subspace has 1 in front of one coefficient of t squared, and this has a 2 coefficient of t squared, right? Or maybe even more easily, you could say, take this guy and multiply it by 3, and then you get 3t squared plus 6t plus 9, but there's nothing in this subset that has a t squared in it, so therefore it's not a subspace. And finally, lucky 7, how about this guy where I have matrices of the form A, 1, 0, B? See if you can think this one through before I tell you. Pause if you like. Well, so you'll see that this 1 again gives you trouble, right? Because if you multiply a matrix of this form by 2, you'll get 2a, 2, 0, 2b. And these things can be any real numbers on the diagonal, but I can't have a 2 here. Okay, so therefore that one's not a vector subspace. Okay? And so now here is a theorem that tells us that one particular thing is always a subspace. Namely, if I start in a vector space and I take the span of a finite set of vectors, so I've got p vectors here, I look at their span, which just means all linear combinations of them, then that'll always be a subspace of V. And why is that? Well, let's take a look at a proof here. It's really easy to see, because suppose that I define H to be this span, right? Well, by definition, that really just means take all linear combinations of real numbers times these vectors, c1 times v1 plus dot 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 plus cp times vp. And now, ask yourself the standard questions. Why is the 0 vector in H? Well, I'm allowed, these ci's can be any values in real numbers I want, so I just might as well make them all 0. Okay? Why is H closed under vector addition? Well, so if I have c1v1 plus dot 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 plus cpvp, and I add it to d1v1, some other vector in here, plus dpvp, then what do I get? The sum will just be c1 plus d1 v1 plus dot 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 plus cp plus dp VP. Okay? So it's clear that, and that's definitely something that's of the form to be in H. Okay, so it's closed under vector addition. And why is it closed under scalar multiplication? Well, that's even easier, right? Because if I take this and I multiply by k, say, instead of c here, then I'll have kc 1v1 plus dot 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 plus kcp vp. And that's clearly of the right form, right? Because multiplying by k, I just use the distributive property. Okay? So that's all there is to it. If I have a finite list of vectors in some vector space, then the span of that, if I look at all the linear combinations, then I always get a subspace of V. And it might be instructive actually to go back to this slide and take a look and see if we can see which of these are spans. So for example, this guy, the set of all AA such that A is in R, if you think about it, this is really just equal to the span of the vector 1, 1 in R2. Okay? How about the set of all things so that F is differentiable? So I don't really know how to do that one as a span. But this matrix, this set of matrices you can think about as really being the span of a couple of matrices. What is it? It's the span of the set. Well, I can have matrices of the, if I take 1, 1, 0, 0, or I can have 0, 1, 0, 1. Right? So if I take any A times this, then I'll get AA 0, 0, and I add to that to 0B, 0B, then I'll get exactly things of the form A plus B, 0B. Okay? This one was not a vector subspace, so there's no hope for it to be the span of something, which would have to be a vector subspace. In example 5, this is really just all multiples, A multiples of t squared plus t plus 1. So in example 5, we've really just got that this is the span of 1 plus t squared. And this is living inside P2, all polynomials of degree less than or equal to 2. 6 was not a subspace, and 7 was not a subspace, so there's no hope of them being a span. Okay, so that's an example of that last theorem. In fact, if you've got a vector subspace, we'll see that we can always write it as the span of a set of vectors, but we haven't quite got there yet. So that's it for video lecture B2. Thank you for your kind attention.